to be sure that
Good morning.
it works. But
yeah, good morning, participant. And some probably in the afternoon. So good afternoon to those participants from the Asia Pacific region. I will chair this session. Actually, this session, strong field of electromagnetic field and gravitational field in astrophysics and early universe. Today, we have 10 speakers, starting from Dennis to Shristi, and we are supposed to end 9:30, by 9:30 in Central European time, in Paris time. So this is the summary of our talk, time schedule. Please check. And I will give you a notice maybe 5 minutes before your talk so that we can have 1 or 2 minutes, 2 minutes for Q&A, all right? Now, Dennis, would you share your screen now?
yeah, wait a second.
Yeah.
Does it work?
Yes, perfect.
All right. So it's full screen now, I guess.
Yes.
Okay. So I guess there's still 2 minutes for more people to arrive. What?
I expect people just join and exit during the session.
Mm-hmm.
On Tuesday session, correct? We have around 30 participants, yeah.
Mm-hmm. Yeah, that was a really nice session.
We have 12 now.
Mm-hmm.
Oh, okay.
It's a bit early for
let me
Central Europe.
introduce Dennis Retcher from Humboldt University in Berlin. He'll talk on gravitational properties of light. Welcome, Dennis.
Yeah, thank you very much. I'm thank you very much also for the honor to open this Friday part of the session. It's a very nice opportunity to present this research direction. And so let's come right to the point. If you have a look at Einstein's equations, then we see on the left-hand side the Einstein tensor, which depends on the metric tensor, and on the right-hand side we have the energy momentum tensor. So to some extent we can say that energy momentum sources the gravitational field. And since light has energy momentum, it must gravitate. But why is that of interest at all? So from an experimental perspective, we can say that with laser light at our disposal in the lab, we have a really great source of light with controllable geometry, energy momentum, and even quantum properties like entanglement. So this would make really great sources of very specific gravitational fields. But unfortunately, at the moment, this is mentally not accessible, at least with current technology. And I will give you some numbers later on. But why is that then interesting otherwise? First of all, it gives us a different perspective on light. The properties of light are inherent in modern physics. They were used to derive special and general relativity, and they are often the basis for alternative spacetime theories. So if we learn something about the gravitational properties of light, we might gain some insight for our understanding of gravity. And we might even learn something interesting for quantum gravity. Now, to start the investigations on the gravitational properties of light, we can start with the model. We assume an emitter and an absorber, and then we assume that there's a one-dimensional light pulse propagating from the emitter to the absorber just along one of the axes without any divergence. So there is no beam divergence. The beam stays one-dimensional. I show the z-axis here for the propagation direction, and here you see this is the energy momentum tensor. So this is really restricted to the beam line. It's one-dimensional, given by these delta functions. And then there is the energy density just along that line, which depends then on the z coordinate and time. Now, if we just consider this to be constant on a certain length, L, then we can call this a box-shaped pulse. And this was the fundamental, basic, simple model that was used for the investigations into this topic in 1931 by Tollmann, Ehrenfest, and Podolsky, and we built on that in a later publication on the gravitational field of laser pulses. Now, for this investigation, we use the framework of linearized gravity. We start by splitting the metric into the flat background metric eta of the Minkowski space in a specific coordinate system where this takes the form -1, 1, 1, 1. And then there's a second part, which is the metric perturbation. And for the components of the metric perturbation, we assume that they are all much smaller than 1. So it's really a perturbation. And this is, of course, only true in the specific, in this coordinate system and slightly around it. So then we assume the Lorentz gauge for the metric perturbation, and we take into account that the trace of the energy momentum tensor for an electromagnetic field vanishes. And then the linearized Einstein equations assume this very easy form. So we have the D'Alembert operator acting on the metric perturbation on the left-hand side, and on the right-hand side, we have the energy momentum tensor. So here we really see that the energy momentum tensor sources the metric perturbation. And this is a wave equation, as we know, is from electrodynamics, and we also know how to solve this in an easy fashion using the method of retarded potentials. So we integrate the source, the energy momentum tensor in that case, with the background line distance dependence 1 over r here. And then, since the energy momentum tensor had this easy form, so there are 4 non-vanishing components that are all proportional to each other, we get the same proper for the metric perturbation. So there is just one function h that we have to keep track of and investigate it. Now, I would like to show you a video of the time evolution of the metric perturbation. First, I would like to remind you of the setup that we looked into. Now, I rotated that setup. Now you have the emission point down here, the absorption point up there, and the light pulse is propagating on the vertical axis from the emission point to the absorption point. And keeping this in mind, now you see the video of the time evolution. So this is the position of the pulse. After the emission, there is a spherical region forming in which the metric is non-vanishing. And then after the absorption, there's another spherical region forming in which the metric perturbation is vanishing again. And you also see the metric higher values very close to the beamline of the pulse. So this is also effect. So you see that, but then also you see that that if we wait for a longer time, so if we push the absorption to future infinity, then the radius of the spherical region becomes larger and larger, and the region close to the pulse will appear as a plane front. Is then approaching the parallel propagating plane-fronted wave solutions that were derived in 9 and 71 by Bonner and Eichelbock and Sechser respectively for the gravitational field of light using solving the full Einstein equations. Now, to understand the meaning of the metric perturbation, however, we need to look into the physical effects, so tidal forces or the geodesic deviation. And this is the relative acceleration between 2 infinitesimally close geodesics. So if you have 2 geodesics here initially infinitesimally close, then the acceleration between test particles is given by this equation down here, containing the Riemann curvature tensor. And since the Riemann curvature tensor is a tensor, it contains coordinate invariant information. In particular, if the Riemann curvature tensor vanishes at a certain point in a one coordinate system, then coordinate system. And so keeping that, we now see time evolution, a video of the time evolution of the Riemann curvature tensor component R0x0x. And you see after the emission, there is a spherical shell forming with non-vanishing value of that curvature component, and after the absorption, there's another shell forming. But the most striking feature here is that these are just spherical shells and not spherical regions, and this curvature component is mostly 0. And that is true for all components of the Riemann curvature tensor here in that situation. So we find the result that non-zero tidal forces are localized in spherical shells. And since these shells expand with the speed of light from the emission and the absorption point, so there is a causal connection between the pulse and these spherical regions during its propagation. Now, this means that the physical effect of light, the gravitational field of light, is and that result that was also found for this full solution of the Einstein equation by Bonner himself in 2009. Since we know this now about the curvature, we can have a look into the acceleration of test particles in the gravitational field of the light pulse. Now, if we consider a test particle at rest in the lab frame in the spherical region, spherical shell due to the absorption, then we find a repulsion effect. And if you place the particle into the spherical shell due to the emission, then we find an attraction. And we find that both effects with the inverse of the distance to the beamline, in contrast to Newtonian gravity, where the decrease is 1 over the distance square, and the acceleration points at the current position of the pulse and not at the retarded position. Light-like test particles, if you place a light-like test particle here in this spherical shell due to the emission, then we find that if it's parallel propagating to the source beam, then it is not deflected. And that is just recovering the original results by Thoma and Ehrenfest and Podolsky, that parallel propagating light beams do not deflect each other. Now, to just give you an idea about the size of these effects, let's consider some numbers. Let's consider the highest power that has been achieved on this planet, 10 to the 15 watts. And we consider a distance to the beamline of 1 millimeter. Then we find an acceleration of 10 to the minus 18 meters per square second. And this acceleration is comparative to the gravitational attraction due to an object of 1 nanogram at a distance of 1 millimeter. So this gravitational acceleration is extremely small. But the gravitational field of light, of laser beams in particular, has one advantage, and that is if we consider a pulse laser beam, so a beam with a repetition of pulses, then also the gravitational field will be oscillating. So, and this oscillation frequency will be given by the pulse periodicity. So this is an oscillating gravitational field, and detecting such an oscillating gravitational field could be a great application for resonant gravity sensors. And indeed, me and my collaborators, Felix Spengler and Daniel Braun from the University of Tübingen, had a look into that, and we considered pulses oscillating in a cavity as a source, or cavities that are periodically pumped, so such that the light in the cavity is recycled, so it's passing the sensor several times. And then we found that the signal-to-noise ratio above 1 can, in principle, be achieved using optomechanical pendulums with very high quality factors. And Felix Spengler already gave a talk about that in the Tuesday part of this session. Now, everything I've told you so far was about light, this very simple model where light is not diverging. So we treated light without taking its wave-like properties into account, which means that light cannot be just focused and not diverging. So if a more accurate model of a laser beam would look a bit like that, this is a Gaussian beam. So let's say we have a laser here on the left-hand side emitting that beam, then it's focused at a certain distance along the beamline to its minimal width, W0, and divergence angle. So it first converges to the minimal width, and then it's divergent again. And only in the limit of this divergence angle to 0, we will obtain this standard model, which also corresponds to the situation of 0 wavelength. So this is the high frequency limit. And in this limit, we, as I said, no divergence, and the light behaves like a fluid of massless particles. And that is the traditional model that was used in most studies of the gravitational properties of light before. We were really interested in the effects if one takes the divergence into account, so finite wavelength. And we looked into, and we derived a perturbative solution in orders of the divergence. Now, in first order, in the divergence angle, we found that the circular polarization of the source beam leads to frame moving outwards from the beam line. Its trajectory would be deflected depending on the helicity of the source beam. So and this, so we just recovered that. But if you now consider a test beam of light in the gravitational field of the source beam, then you find that it's, and so this rotational polarization of the test beam would depend on the polarization direction, so the spin angular momentum direction of the source beam. So here we find gravitational spin coupling of light. We found that if you now consider a test particle that is parallel propagating to the source beam, that there is a rotational polarization as well. These effects can be enhanced by using an optical cavity for the sensor beam, so the test beam as well. So, for example, a linear cavity for the effect in particular, this is a gravitational Faraday effect. So it is a non-reciprocal effect. If the light propagates along the same spatial path back and forth in a linear cavity, then the effect would accumulate, and one could enhance strongly this effect. So we can also put in some numbers here to find to see what the size of this effect is. And if you use again 10 to the 15 watts, and we consider a beam focus of 1 micron of the standard lasers in this case, and so this is basically the optimum you can focus it to, and the divergence angle of 0.3 rad, and a finesse for the test beam cavity of 10 to the 6, which is also quite high, then we find a rotation angle of 10 to the minus 32 rad. Now, to put this into perspective, we compare this to the best sensitivity that is in principle achievable in the interference sensor scheme on the test beam. So assuming, so this is given by 1 over the square root of the number of photons in the cavity and the number of measurements. So assuming 10 to 15 watts for the driving power of the test beam cavity. So this is outside of the cavity. Inside of the cavity, this will of course be enhanced by due to the high finesse, and a number of and a total measurement time of 1 week. We obtained minimal or best sensitivity minimal error of 10 to the minus 15 rad, and you see this is still 17 orders of magnitude away from the effect. Yes, so that focused light beams start to deflect each other even if they are parallel propagating. So this is contra Podolsky. However, this is only the case if the two beams overlap. But in any case, we found that focused light gains some properties of massive matter. That was already something that was shown for the effective propagation of light in focused laser beams in 2015. So this turned out to be slower than the speed of light due to the focusing of the beam. Now, in summary, I've told you that streams of null fluids and massless point particles do not deflect each other if they're parallel propagating. This is the original result. The gravitational field of laser pulses in vacuum, if we consider zero divergence, are confined to spherical shells associated with the emission absorption with the inverse of the distance to the pulse. I also told you that for a focused laser beam with circular polarization, we find frame dragging and a rotational polarization of test beams. So this is gravitational spin-spin coupling of light. And I told you that parallel propagating beams indeed deflect each other if we take the finite wavelength into account. Now, what I didn't tell you about is that I didn't tell you anything about frame dragging due to a ring cavity, frame dragging due to beams with angular momentum. I didn't tell you anything about due to the emission of light and the relation to light rockets. I didn't tell you anything about the field of plane electromagnetic waves, or about photon-photon scattering and perturbative quantum gravity, and so on. The phenomenology of the gravitational properties of light is really rich, and I hope I convinced you that this is a really interesting research field to look into. And now I would like to thank you very much for your attention, and I would for your questions if you have any.
Yeah, thank you for your talk. Very interesting talk. Any questions from the audience, participant? If you have any question, please unmute so that we can hear your voice. I cannot hear you. Can you use the button mute? Dennis? Dennis, can you hear me?
Yes, I can hear you.
There seems to be no question. What about the
it's maybe a bit too early.
Yeah, I know, understand. But you consider only gravitational effect of impulsed pulsed electromagnetic wave, and that is a kind of the gravitational interaction with the electromagnetic field, but there must be photon-photon type interaction, strong field QED effect. Do you have any comment on that?
Yeah, I think this is also quite interesting, right? So if you really want to have a strong gravitational effect of light, you need really strong light sources and strong light pulses, and then, of course, if you go to extremely high field strength, then you will get these effects of nonlinearities, right? That you are referring to, right? Yeah. Yes. And then at some point, this will also play a role, and everything will mix up. So you will have these photon-photon interactions, and at the same time gravitational interactions and gravitational fields. And then I guess it becomes even more interesting at some point, because then also if you come to the Schwinger limit, right? But I think we are a bit away from that still with laser sources at the moment. But certainly.
Question from Eshigar Padi.
I think we are away from the Schwinger limit, right?
Would you ask a question? Eshigar Padi.
I was just clapping. I wasn't asking a question.
Okay.
All right. Yep. Then shall we move to the next talk by Matteo Tombrini? Are you ready for your talk? Would you share your screen?
Can you see the screen?
Yeah.
Okay, yeah, excellent. So good morning, everyone. First of all, I would like to thank the organizers for inviting me and for the opportunity to talk here today. In my talk today, I will show you some recent developments in laboratory-based intense gamma ray and electron beams for strong field QED and laboratory astrophysics. In these slides, I have summarized some of the typical setups for this kind of studies for both strong field QED for the generation of intense gamma ray beams or even electron-positron pairs. The typical one, the most traditional one, involves electron beam colliding with counterpropagating laser pulses. Something proposed more recently involves the string instabilities in electron beam plasma interaction or beam-beam interaction. And in this talk, I will focus mostly on these very recent developments published this year, which involves the interaction of electron beam with multiple foils. I will show you that this leads to beam focusing and to the production of gamma rays. And at the end, what is possible, what is enabled by this kind of geometry is the generation of extremely dense, so solid density or and above electron beams and gamma ray photon beams. Now coming to the outline of this talk, I will first give you an introduction with the motivation for intense particle beams. I will very briefly review what are the strong field QED processes, and I will come to the generation of extremely dense electron and gamma ray beams and which new opportunities for extreme plasma physics and laboratory physics, astrophysics are enabled by this kind of beams. At the end, I will give you an outlook of the current research and a summary of my results. So what are the motivation for extremely intense high energy photons or lepton beams? So we all know, for instance, that the quantum vacuum is not really something static, it's a dynamic, it's filled with virtual particles. So these virtual particles pop up. How can we detect these kind of effects? Well, if you have, for instance, a high energy gamma ray beam, so very intense, we can prove the nature of quantum vacuum, for instance, with birefringence, dichroism in strong electromagnetic fields, and we can do, for instance, photon-photon physics and biostandard model physics. In fact, these virtual particles enable the fact that photons can scatter elastically, which would be impossible in classical electrodynamics, or photons can convert into matter, for instance, electron-positron pairs. More interesting is that photons are their own antiparticles, so they can even produce some unknown particles. So this could enable study of physics beyond the standard model. So with dense electron beams, what we can do is at least a couple of studies, which are very important. One is to prove strong field QED with a single beam. I will talk you in more detail later, but essentially what you have is that if the beam is dense enough and you send it to a dense plasma, you can generate automatically very strong electromagnetic fields. And of course, astrophysics, there are many astrophysical environments which are filled with electron-positron pairs. For instance, around compact objects, we know very well that, for instance, around black holes, around pulsars, these compact objects are the engines that power these powerful jets that are emitted. They are extremely long. These jets are mainly made of electron-positron pairs and gamma. Of course, there are also other components, but this is one of the most fundamental one. It would be extremely important to study the collective dynamics of these electron-positron pairs in the laboratory, in a controlled environment, to reproduce mechanisms that are similar and are of interest for astrophysical environments. So where this is possible, for instance, I would like to mention this facility. So I would like to stress the fact that we are really in the perfect time to start this kind of studies, because new facilities are coming up. I will mention just one because I'm limited with time, which is the FESET-2 facility. And what is extremely interesting in this facility, I don't have time to go into the details, is that they deliver like 10 GeV electron beams, so energetic beams, with a lot of charge, 2 nanocoulombs, especially they are very compressed, so micrometer scale. So we now have the possibility to have these very well collimated energetic bunches of electrons or even positrons that we can send to a target. Of course, since these electrons bunches are extremely dense, they have very strong self-fields, electromagnetic fields. I will show you how we can make good use of these kind of beams. Now, very briefly, just to summarize and to fix a little bit the language, what are the basic QED processes in a strong background electromagnetic field? So the first one is the most simple, like we have an electron or a positron and background field here. The electron interacts with this background field and emit photons. Very simple. The other one is that we have a photon, and this photon interacts with the electromagnetic field, and it converts into electron-positron pairs. And normally, these kind of processes are controlled under large conditions that are relevant for laboratory, just by one parameter, which is the so-called chi parameter or the quantum parameter chi, which from the physical point of view is just the ratio of the electric field experienced, for instance, by the electron in its own rest frame in units of the Schwinger field, so the QED critical field. Now, what happens if this parameter becomes comparable to unity? In the case of an electron, in this case of this process, what will happen is that the emitted photon energy is comparable to the initial electron energy. In the case of a photon, if this parameter becomes comparable to unity, then the photon conversion into electron-positron pair becomes probable. So there is really a chance that we create a lot of these pairs. Now, coming to the main topic of this talk. So we all know that if you have an electron beam, even dense, but it is ultra-relativistic, its motion is nearly ballistic. And the reason is that there is a simple relation, at least for a cold beam, between the electric and magnetic field, which when inserted into the Lorentz force implies that the transverse electric field, the radial field that will lead to beam expansion, are strongly suppressed by a factor gamma square. Now, the point is when instead we have a conductor close to the beam, such as in this situation, suppose we have a beam colliding with a perfect conductor here. Now, if the conductor is pancake shaped, which means it is more elongated than longitudinally extended, and in the limit of infinite conductivity for the conductor, then this process, it can be proved exactly, I will show you where, it can prove exactly that this can be visualized as a beam colliding with its image charge. So we have a kind of a collider but with just a single beam. In fact, what happens is that the conductor is capable of screening completely the transverse electric field and amplifying, so making the magnetic field twice its field. So we can immediately understand that this will lead to some pinching force, so the beam will be focused, plus there will be, because of this uncompensated field, some emission of gamma ray photons. So and if the beam is dense enough, we really have the opportunity to reach chi of the order of 1 or even well above. So we are in the condition to probe strong field QAD effects in the laboratory. And then as each single photon emission, we carry away a significant fraction of the initial electron energy. Now, since we started this with a single foil, what happens if the idea is simple, what happens if we have multiple foils? So we can have the electron beam interacts with the first foil, undergo some focusing, emitting radiation, then this will have even a stronger field because now it's focused, the field is stronger, then interact with the second foil, further compresses, and then so on, and emit further radiation. So at the end, we end up with a focused electron beam, extremely focused, and dense gamma ray beam. So can we actually see this in the laboratory? Can we make use to generate beams with unique properties in terms of density and extremely efficient? And now, if I will show you the results of this kind of interaction, here I present the results of 3D, fully three-dimensional peak simulation with the parameters that are very similar to those that will be available at the advanced stage of SF2. Oh, sorry, at the advanced stage of SF2. And this beam, which is of micrometer size, more or less, it interacts with 20 consecutive aluminum foils which are sub-micrometer thickness, and they have this 10 micrometer interfoil distance. So here you see in this upper panel, here we plot the transverse electric field of the beam. In this upper right panel, the transverse magnetic field, and here in this lower left panel, the electron beam density. In this right panel here, I will show you what I report is the photon beam density. Of course, at the initial time, we have no photons, so it's completely empty. We just have the electron beam with its own self fields. Now, what happens if we let it interact? So we let it evolve. Okay, at this stage, you see the beam has interacted. This is the first foil. You see immediately there's a suppression, the cancellation of the electric field and amplification of the magnetic field, and the first photons are generated. If we let it interact further, again, with the second foil, you see again, this effect is repeated, so suppression of electric field, amplification of magnetic field. You start to see that there are some photons building here, so the density is rising, and simultaneously you see that the beam becomes increasingly more dense. What happens at some point is that the beam becomes so dense, this stage, that is denser than the foil itself. So it's denser now, the electron beam is denser than a solid, and this implies that the solid is not able anymore to screen these fields, but anyway, this field penetrating inside the target are extremely strong. So again, the beam, electron beam, a fraction of the beam is interacting with extremely strong fields here in this channel created by the field itself, and the photon beams is still increasing its density. And as we let it propagate with further foils, you see again this effect to continue. So there is a channeling. What happens is the electron beam starts to be modulated longitudinally because there are the field affects differently the front of the beam to the rear of the beam. So we have a modulated, extremely dense electron beam plus an extremely dense photon beam. If we now go, for instance, after to the final stage, so to speak final, we just consider just 16 foil. just the interaction after the interaction of 16th foil, what we can see, if we have here a density plot for the electron distribution, this is actually the logarithm of the density distribution. So there are huge changes of orders of magnitude. And we see that at the center of this beam, we have 2 orders of magnitude beam density increase. So we have gained 2 orders of magnitude in the beam density after the interaction just with 16 foils. And we have also here, this is the density plot, the logarithm of the density of the photon density. We have seen that we have generated also an extremely dense photon beam. This beam, this gamma ray beam density beam has a 5 milliradian aperture, so it's very well collimated, just 4 femtosecond duration, and a peak density which is larger than that of a solid. And if we look to the how the efficiency evolves as a function of the number of foils, this is the efficiency as a function of the number of foils of the interaction. We have this phase, this kind of more or less linear behavior of where at each foil interaction we continuously gain more photons, but more or less linearly of the order of few percent. And this is until the foil is capable to reflect the fields. When you go to the stage where the beam density is larger than that of the foil, then we have a sudden jump here. You go to the channel. This chi parameters becomes larger than unit, becomes of the order of 3, and we still extract energy from the electron beam. At the end, after just 20 foils, we have more than 30% conversion efficiency from the electron beam to the gammas. Now, let's go to the outlook. So what can we do more? Now we have a very dense electron, generated very dense electron and also positron beams, but we would like, for instance, for laboratory astrophysics, we are interested into studying pair plasmas. They are of primary interest for fundamental plasma physics and for astrophysics, and they behave differently, radically different from traditional plasma, where we have a big asymmetry between the electron mass and the ion mass. And this kind of plasmas, so electron-positron plasmas, dominate the dynamics, the matter content of many compact astrophysical objects, pulsars, magnetas, for instance, but also black holes. So it will be extremely interesting, as I said at the beginning, to study them in the laboratory. So the generation of quasi-neutral gamma electron-positron plasma extending over several skin depths in the laboratory in all directions would allow for the first time to probe a new regime dominated by the interplay between strong field QED effects and collective plasma dynamics of relevance for extreme astrophysical environments. And the current work that we are developing is to use these extremely dense beams that we have generated with the method of the multifoil to create this kind of electron and positron beams. I am showing you some preliminary results. So these are still preliminary, showing the formation of electron and positron beams, again, with density comparable with a solid. And we think that this will be a very nice route for the generation of this unique plasma towards the exploration of electron-positron beams, collective properties in the laboratory, and to probe and to run experiments of relevance for astrophysics around compact objects. Now, before concluding, I would like to just mention something in a slightly different topic, and I would like to point out that the extremely high energy regime, so where chi becomes really much larger than 1, a strong field QED is almost untested and poorly understood theoretically. It has been conjectured that QED becomes strongly coupled, so basically you replace alpha with alpha chi to the 2/3 in the coupling as an effective coupling. And so around the chi 1600, then we have that the strong QED would become, strong field QED would become a strongly coupled theory, such as quantum chromodynamics. And this is how similar to what happens with Z ions, where we have alpha is replaced by Z alpha, and this would be that 137. So what we would like to point out is that already at this regime where chi is much larger than 1, but still not so extreme, there are new qualitative features that appear in the photon emission spectrum, because the electron to photon energy conversion with a single photon emission becomes really efficient. And this enables the possibility to create a laserless gamma collider from electron collider. And the feature that I'm mentioning is here. You see that there is a peak in the photon emission spectrum. This could be used in this kind of setup where we have 2 asymmetric beams, one probe beam which is very energetic and probing the fields of another counterpropagating fields in a very precise way. And this could allow precision studies of strong field QED, because there is a one-to-one correspondence between the peak, this peak that we generate in the photon spectrum, and the quantum parameter, which is reported here in this formula. So we could know exactly what are the fields experienced by the beam and perform precision studies, and also use this efficient conversion of electron energy to photon energy to realize a very collimated, extremely energetic gamma beam, for instance, for a photon-photon collider. Now, coming to the summary of my talk, I've shown you that intense gamma ray electron beams open new avenues of research in strong field QED, plasma physics, high energy and beam and high energy density beam physics, photon-photon physics, and relativistic laboratory astrophysics. So the synergy between plasma and strong field QED effects enable really unique, enable the efficient generation of gamma rays, and which have really unique properties in terms of flux, intensity, and energy. And following this recent theoretical and technological development, a new class of experiments at extreme fields are underway. So will be possible experiments, for instance, phase-2 are expected to start this year. So we are really close to the beginning of these new exciting areas of research. And there we'll be able to study the interplay between strong field QED and collective effects in a dense electron-positive pair plasma. And I would like to thank you for your attention. I'm open to questions.
Yeah, thank you for your very interesting talk. Any question from the audience, from participant? Oh, yes, Dennis.
Yeah, so you present this picture of these aluminum foils, and you also said something about infinite conductivity. Is that was that just an example where for a limit, or are you assuming this all the time? Because I'm not sure if I have no idea how accurate this assumption is.
Okay, so this about about the infinite conductivity is just for analytic calculations, which I have not shown here because of course time is limited. But so this is just an assumption for analytic calculation. So it is possible, in assuming that the foil is a perfect conductor, to perform exact analytic calculation of the field which is generated by this foil itself. And this is possible to use to demonstrate that in this limit, the beam foil interaction is like a beam colliding with its own image. But this is just for theoretical, so for making analytic predictions really analytic. Okay, but when we come to the simulation, so this kind of simulation that I reported here, there is no such assumption. So it's really a plasma with its collisions included. So there is resistivity included. So in this sense, in fact, of course, the reflection is not perfect. The field does not really become twice the field. So there are imperfections, but this is treated exactly in the numerical simulations, but for analytic purposes. We relied on this assumption of perfect conductor for making the analytic calculations.
It sounded like now, as you said, it is very close to that limit, though, right? So it sounded now because you said
the foil. I mean, a good conductor behaves very close to a perfect conductor, very close. Mm-hmm. So I mean, instead of getting, for instance, a factor of 2 in terms of amplification, so the magnetic field is not twice, but it close to 1.9 times. So there is really an amplification. It's not as a perfect conductor, but very close to.
Because I would assume that this kind of also depends on the velocity of your of the electrons, but they are anyways already relativistic, I guess. Or
no, it's already relativistic. It is a 10 GeV electron beam, so the gamma factor is 20,000. So it's extremely relativistic.
Any other question?
So if there's no other question, I would have a second one.
Please go ahead.
But I could wait. If there's some other question, then I would wait.
A short question. Yeah.
Okay, so my second question would be: you showed these. You said that these electron beams are extremely dense, like in a solid. So what happens due to the repulsion of the electrons? Also the repulsion between the electrons. Is there any effect of that already visible?
So the point is the following. So at the beginning, they are not first. So you start with a beam which is not such as you get that after the interaction with multiple foils. And the point is, of course, there is an effect. So, so there is the first effect, which is this one. So the relativistic one. So as long as the beam is very relativistic, the effect of the expansion is suppressed. So there is, but it is suppressed. So it means that it has to travel some distance. The second thing is that often, so what we have, for instance, to generate these electron-positron pairs, which I shown here some preliminary results, this is the original electron beam, very dense, is that the electron beam at this stage, even though it's not shown here, is interacting with the plasma. So it's inside the plasma. Now the plasma itself is reacts to the fields of the electrons. So it creates, for instance, a charge separation. So it creates some fields that are actually focusing. And these fields are focusing, and you see here, for instance, already in this picture here, because the electrons that we have generated from the photons, so this beam has emitted photons. Photons have converted inside these strong fields inside the plasma into electron-positron pairs, and these electrons are actually focused by the fields, which implies that the positrons, because of the opposites, are actually tend to the focus. But it means that inside the plasma, the dynamics is so in a vacuum, if you let it propagate enough, of course, they will expand. But in a plasma, the dynamics is much more complex, and the field itself could even do the opposites, could focus the electron beam. For instance, if you have a very dense electron beam expelling all the electrons from the plasma, you have a charge separation positive by the ions, and the ions attract compensate for the electric field of the electron beam. So in vacuum, yes, the beam would expand.
Matteo, thank you for your answer.
For the questions and for
yeah, thank you very much. Very
Yeah.
fascinating.
Thank you.
Very interesting. Shall we move to next talk? Alexander Brief, would you share your screen?
Yes. You can see my screen.
Yes, yes. Perfect.
I can start my talk. Let me present to your attention my talk is devoted to research the vacuum instability effects in strong field in QED with a symmetric electric field of analytical form. This talk is based on the preprint of our article. Particle creation from the vacuum by strong electromagnetic and gravitational fields is a remarkable effect predicted by quantum field theory. Quantum field theory with external backgrounds is to a certain extent an appropriate model for theoretical study of the effect. In the framework of such a model, the particle creation is interpreted as a violation of vacuum stability. Creation of charged particles from the vacuum by electric-like fields needs super strong field magnitudes compared with a single critical field. Nevertheless, recent progress in laser physics allows one to hope that this effect will be experimentally observed in the near future, even in laboratory conditions. Electron-hole pair creation from the vacuum, analog of the electron-positron pair creation, was recently observed in the graphene by its indirect influence of the graphene conductivity. The graphene conductivity modification due to particle creation was recorded by Gavrilov-Gitman mechanism. Depending on the structure of external backgrounds, different approaches for neperturbative calculation effects of the vacuum instability in QED with strong backgrounds were elaborated. The most consistent formulation of the particle production problem is formulated for time-dependent external electric fields that are switched on and off at t tend to plus or minus infinity. The formulation it is based on the existence of exact solutions of the Dirac equation with corresponding external fields. When such solutions can be found, and all calculations can be done analytically. We refer the examples and exactly solvable cases, usually considered non-stationary homogeneous electric fields of constant direction. Electromagnetic vector potentials of such fields can be chosen as the time-like potential steps. Scalar potentials belong to zero. Therefore, we can fields of this type electric potential T steps or simply T steps. Until now, there are known only few exactly solvable cases in strong field quantum dynamics with T steps. Here we present a new exactly solvable case of this kind and compare it with the already known cases. The homogeneous fields with constant direction are considered in d dimensions parameterized by coordinates x. The electromagnetic potentials can be chosen as time-like steps. This figure shows a general view of the electric field red line and its vector potential blue line. The first example of exactly solvable cases is a T constant electric field. The field corresponds to a regularized version of the constant field. The vacuum instability in the T constant electric field was studied in Vaglov, Gitman, Schwarzson, and Gavrilov-Gitman. The vacuum instability in the lateral field was studied in Schwinger and Nikishov. Next example is Sauter-like electric field. The vacuum stability in the Sauter-like electric field was first studied by Nalovny and Nikishov, and then many researchers returned to this problem, since in the case under consideration, it was convenient to test various approaches. Next example, Cauchy's exponential peak electric field. The field is exponentially growing and decreasing electric field. Electric field is red line, and its vector potential is blue line. The vacuum stability in the exponential peak field was studied under Gavrilov-Gitman and Gavrilov-Gitman-Shishmarev. Next example is the universally square peak electric field. The inverse square peak field is a combination of two parts, one increasing and another one decreasing, both of them inversely proportional to square of the time. On next slide, you can see figure inverse square peak field and its vector potential. The vacuum stability in the inverse square peak field was studied in Gavrilov-Gitman. We note that among the above exactly solvable cases, only the Sauter-like electric field is given by analytical function. Here we present a new example of exactly solvable case of such type. In contrast to the Sauter-like electric field, this field is asymmetrical with respect to time instant t max, where it reaches its maximum value, E max. This slide shows this electric field and its vector potential. It is useful to compare analytic asymmetric electric field and Sauter-like electric field. We present a figure of both fields. Analytic asymmetric field with sigma, parameter sigma by green line, and the Sauter-like field shifted to right in time by red line. We know that the time from minus infinity to T max, both fields behave is a very similar way. This slide shows the Dirac equation in the external electromagnetic non-stationary field. The quadratic Dirac equation is reduced to a linear second-order differential equation by a scalar function phi. A completed set of solutions to this equation is required to construct the in and out solutions they needed to study vacuum instability in this field. In and out solutions, psi of the Dirac equation have special asymptotics as t tends plus minus infinity and correspond to initial minus and final plus particles and antiparticles. The functions phi that correspond to spinors psi that correspond to spinors psi that are in solutions are denoted by zeta phi, while functions phi that correspond to spinors psi that are out solutions are denoted by zeta phi top zeta. While both sets are classified by a quantum number zeta, which labels particles zeta equal plus which labels particles and antiparticles zeta equal minus. Solutions have the following asymptotic behavior. We will seek solutions to the quadratic Dirac equation in the following form. Then we obtain Hahn equation for function u. We will find exact solutions of the Hahn equation as follows. Note that the operator identity holds. Whence it follows that if the solution is substituted in the form function u into the equation, that it becomes identity if the function W satisfies the hypergeometric equation. This operator corresponds to hypergeometric equation, operator L. Moreover, if the linear independence of the solutions of the hypergeometric equation implies the linear independence of the solutions
Alexander, you have 3 minutes.
Yes. Independent the solutions of Hahn equation. This method by different from the change of variable in the equation, and it can be carried as a generalized double transformation using the operator M. Next, we can see the in and out solutions. Next, using exact solutions that were found above, we already can calculate characteristics of a vacuum instability in the electric field, namely the vacuum to vacuum transition probability PV, differential, and total main numbers of created parts. Let's analyze the dependence of calculated quantities on the parameter sigma. We determine the shape of the analytic asymmetric electric field. We consider small values of the parameter sigma. In this case, the analytic asymmetric electric field can its potential change rapidly, and the electric field is short pulse corresponding to small increment delta W. Next, we consider the big sigma, and we have one contribution to created parted. Then I read the final remarks. One of the important results of the work is the original approach to solving the Dirac equation in the symmetrical field and the construction of the corresponding in and out solutions. With the help of the solutions, basic characteristics of the vacuum stability are calculated perturbatively, namely the vacuum-to-vacuum transition probability, differential and total mean numbers of created parts. The obtained characteristics of the vacuum stability in the analytic asymmetric field were compared with one obtained in other exactly solvable cases. Well, it's all I have to say. Thank you for your attention.
Okay, thank you. It is an interesting result in non-trivial background of electric field. Any question from the participant? A short question. If not, then shall we move to the next talk? Yeah, thank you, Alexander.
Yes.
Now the next speaker is Stefano Campion. Stefano?
Yeah. Can you hear me?
Yes.
Oh, okay. I will
Share
try
your
to share my
screen. Yes.
Can you see it?
Yes. Yes.
Okay. So, good morning to everyone. In this talk, I will present part of my work that I did during my PhD within ICRANet and University of Sapienza. And I will talk about the magnetic field screening in a strong crossed electromagnetic field. So, let's start giving the basic relation that we base our model. We built a theoretical toy model that we can apply in different physical fields. So the principal relation is proportionality between the electric field and the magnetic field with this constant epsilon that we call it spin, and the sum value between 0 and 1. We call it spin because we would like to apply in a further study to the case of GRB and practically, and this relation holds in gamma ray bars near the black hole, where as explained by the Wald solution in 1974. So the basic steps of the screening process are the following. We have a huge amount of electron-positron pairs created by, for example, vacuum polarization process. They are accelerated by the electric field and start to emit synchrotron photons that interact with the background magnetic field, and we mean the magnetic pair production process, and start to create new pairs. And these pairs circularize around the magnetic field lines and create an induced magnetic field in opposite direction to the background one, and then screening it. So the assumption that we use to build our model is we use a one particle equation, and then all the particles have the same are subject to the same dynamics, and namely have the same trajectory and velocity. And we use Minkowskian space-time this proportionality between the electric and magnetic field, and we assume the perpendicular field with magnetic field aligned along the z-axis and the electric field aligned along the y-axis. So this assumption and the semi-classical approach, also the Minkowskian space-time, are honest, since the case for since we have strong fields, all the particles are forced to have the same dynamics and then follow the same trajectory. Also, the integration time where the screening occurs is very short, between 10 to minus 21 and femtosecond, and so where a Minkowskian spacetime can be assumed. And also, this corresponds to a very small scale between 10 to minus 11 and 10 to minus 5 centimeter, where this proportionality between the two fields can hold. Sorry. And finally, we verified that for these conditions, quantum effect can be negligible, since the Broglie length for the electrons is smaller than the Larmor radius, and also the energy applied by the electric field to the electrons is smaller than their rest mass energy. So the semi-classical condition can be applied. But this condition, as we write here, impose some initial value for the gamma factor of the particle and the initial magnetic field, as we will show later. So I describe the equation of the model. So we have a particle, the equation for the particle dynamics, and the equation for the emitted radiation described by Kellner in 2015, where this H bar described the different emission during different region of the particle, namely can describe the radiation during bicurvature emission, synchrocurvature emission, and synchrotron emission, where chi is the ratio between the photon energy and the electron energy. So we need also two equations for the creation of the photons and creation of pairs, and these two equations are coupled. Indeed, for the equation for the number of photons, this is proportional to the number of pairs, and the rate of the photons emission, namely given by the luminosity and over the photon energy. Instead, for the equation for the production of the pairs, this is proportional to the number of photons, to this factor RAE, that is the initial coefficient for the magnetic pair production, and the velocity of light, that we call it this factor, we call it zeta, and that gives the pair production rate of the magnetic pair production, that for perpendicular field is given by Doherty and Lerck in 1970, that after some mathematical process that to bring the equation to our physical system, assuming this final formula where eta y, eta x, and eta zeta are the direct or cosine of the photons, written here, where theta and phi are the emission angle of the photon. So this condition is valid until psi is more or less than 1. Psi, it's only the 1/2 times the photon energy normalized to the electron rest mass energy times the magnetic field normalized to the critical fields. And so finally, we need to be we built an equation for the screening of the magnetic field, and starting from the Biot-Savart law. We have the current, the perpendicular current created by the electrons, and after some geometry, we get this final equation that, as we expect, is proportional to the perpendicular velocity of the electron, the curvature radius inversely proportional to the curvature radius of the particle trajectory, and to the pair production rate. So, as we stated, for the validity of our assumption, we need to choose a specific initial condition that we summarize in this table. So the condition for the classical approach imposes this value for the gamma factor of the particle and the magnetic initial magnetic field, the background magnetic field. So we also choose different value of the spin, 1 over half, 1 over 10, and 1 over 100, and different direction of emission of the particle along the y-axis, along the z-axis, and along the generic axis. That is characterized by a polar angle of 75 degrees and azimuthal angle of 30 degrees. We also choose different number of initial particles injected in the system. And here we show the result of our the integration of the system of equation. On the left, we show the result for all the direction of emission for all the value of the spin for 10 to 10 particle. And we see that, as we expected, the screening is higher for particle that has a greater component of their perpendicular velocity. As for example, here the green dashed line corresponds to the particle emitted along the y direction. So, and also here for the spin 1 over 10 and the same. And also for a spin 1 over 100 the same. Instead, on the right, we show this is for 10 to 10 initial 10 to 10 particle. If we inject more particle, for example, here we have 10 to 15. We see that the screening naturally is higher, since the equation is proportional to the rate of reproduction. But we cannot put more than 10 to 15 particle. Since there are, in this case, the semi-classical approach are no longer valid, and the quantum effect start to act. On the left here we show the gamma factor of the particle and the photon emission, and we see the coils produced by the particle along the magnetic field lines. And on the right the photon emitted for a different value of the spin, and for 10 to 3 particle continuous line, 10 to 6, and 10 to 10. So there is an exponential growth of in very small time of the number of photons produced. And we show just simple the coils in a 3D and the projection on XY plane. So summarizing, we have built a toy model that describing the magnetic field screening, and we see that it depends by some initial condition as the number of initial particles emitted, the initial emission direction. We notice that the screening is higher for a particle with a major component of their velocity, perpendicular velocity, and from the parameter, the constant of proportionality epsilon. Indeed, fixing epsilon, the screening is stronger for beta perpendiculars higher. Fixing the y direction, for example, the screening increase if we increase epsilon, and fixing the g direction, the screening increase if we decrease epsilon. And this behavior can be described by how the parameter enter in the equation, and due to the proportionality to the perpendicular component of the velocity. So since this is a simple toy model, we will proceed for further study to studying different configuration of the field, not only perpendicular, studying also over critical field where the semi-classical approach is no longer valid due to the presence of quantum mechanical effect. And also we would like to apply this model to black hole and gamma ray bursts in order to screen the strong magnetic field in gamma ray bursts, and in order to allow to photons to leave the system freely without interacting with the magnetic field. So thanks for the attention.
Thanks for your talk. Any question from the audience, participant?
I have a question, if I may.
Yes, yes, please.
What do you think would happen when the magnetic field becomes stronger than the quantum critical field? So what kind of strong field QED effects do you expect to become important?
We're going to study it. we still didn't do it. It's part of my PhD. My PhD I didn't have time to improve this future. But as I stated here, for
Actually,
our critical
I
field.
know about that question. When the strength of
Oh.
magnetic field increase, actually production increase.
Yeah, but we have also for
Function of intensity of magnetic field.
As we said here, for stronger field, that is conditioned for the Broglie length and the energy on the emitted by the imposed by the electric field is not for stronger field and no longer value. So surely there are problems or with the Landau levels.
Purely understood, but actually, photon scattering with the magnetic field can produce the electron-positron pair, purely QED effect. So it can apply. There already literature there.
Yes. But obviously, for the equation that we have built in our model, in the case of stronger field, are no longer valid. So
yeah, I know. But any other question? If there is no more question, then let's thank Stefano and move to the next talk. Sylvia Pla, would you prepare?
Yes, can you hear me?
Would you share your screen?
Yeah. Okay, I'm trying to do it. Okay, so now I'm sharing.
Yes. Would you increase the volume of your microphone?
Oops.
Yeah.
I don't know why it maybe now is better.
Oh yes, better.
Okay. So I'm going to start. So my name is Silvia Pla Garcia. I'm from the University of Valencia, and here I'm presenting the talk New Partial Summation of the QED Effective Action. And this talk is based on a recent published paper written in collaboration with José Navarro Salas. Okay, so today I will talk about a conjecture that we have proposed some months ago that states that the proper time expansion of the one-loop effective Lagrangian for quantum electrodynamics can be partially summed in all terms containing the field strength invariants F and G. And I know that the statement sounds complicated, so let's see what this conjecture exactly means. So here you have the overview of the talk. And before starting with the conjecture, I would like to review some basics. So to this end, I will introduce some important things related with the one-loop effective Lagrangian for QED. Then I will briefly talk about the one-loop effective Lagrangian, but now in presence of gravity, and about some ideas that we can borrow. And after this, I will finally explain the conjecture, and I will comment some consequences, and finally, I will give a brief summary of all the above. Okay, so let's start. As you may already know, the Heisenberg-Euler-Lagrangian describes the nonlinearities of quantum electrodynamics when the fermionic degrees of freedom are integrated out and the electromagnetic background is constant. It was originally proposed for fermions, but it can be extended to scalar quantum electrodynamics. So the Heisenberg-Euler-Lagrangian is usually written in terms of the so-called proper time parameter S, But apart from this, can be written in several ways. I have chosen this convenient form that you see here, borrowed from the Parker and Tom's book, with this matrix F, and what you see in the formula is the formal or the unrenormalized version of the scalar Heisenberg-Lagrangian. So these quantum corrections to the classical Lagrangian have important implications, such as like Rayleigh scattering, vacuum polarization, recreation, etc. And as I said before, this result was obtained for constant background electromagnetic fields. But in general, when the background is non-constant, the formal expression of the one-loop effective Lagrangian is not known. However, it is always possible to make an asymptotic expansion of it in terms of the proper time parameter S. This expansion consists of an expansion in the number of external fields and the number of derivatives, and contains some general behavior of information of the unknown formal one-loop effective Lagrangian. So here you can see how the proper time expansion looks, and I have written here the first coefficients of expansion, which look pretty simple, but I have to say that as soon as we increase the order of the expansion, the coefficients became more and more involved. And I would also like to stress that the process to build this expansion is not trivial, and that it is required hard technical work to obtain the coefficients in the final form. Okay, so in the same way that one can look for quantum corrections in electrodynamics, it is possible to do it in presence of a gravitational field. That is, to compute the one-loop effective Lagrangian when the background field is the gravitational field. As you can imagine, it is a difficult task, and in general, the one-loop effective Lagrangian is also, in gravity, is also unknown. However, as in the previous case, it is possible to make a proper time expansion of it with the general form that you see again in the screen. And these AM coefficients are the so-called David coefficients, and they are very involved because they depend on the scalar curvature, the Riemann tensor, the derivatives, and so on. And here I would like to say that this expansion is very similar to the previous one, but they have been computed using different methods. In the previous coefficient, the previous coefficients have been obtained using the so-called string-inspired method in the wordline formalism, while in this case, they came from the expansion of the heat kernel. Both expansions are related by total derivatives, so we can say that they are equivalent. So as I said, the one-loop effective Lagrangian in gravity is in general unknown, but there is one case where it is known, the case where the background field is the static Einstein universe. So in this case, the one-loop effective Lagrangian is this one. So here, we have to replace the function g by this result here. So now it comes the interesting part, because from this result, Parker and Toms propose a new adiabatic expansion for the general one-loop effective Lagrangian defined by this relation here. So this is the old adiabatic expansion, and this is the new adiabatic expansion. And here you have more explicitly the explicit form of the new adiabatic expansion. So this is the new adiabatic expansion, these are the new coefficients, and here we have extracted like an exponential factor. And the key point here is that this new adiabatic expansion has an important advantage with respect to the usual one. These new coefficients do not contain any term that vanish when the scalar curvature is replaced by 0. And it means that with the exponential factor, we have captured all the dependence on the scalar curvature. And this result is interesting because it has encapsulated a general non-perturbative behavior of the one-loop effective Lagrangian for arbitrary gravitational background. So with this idea in mind, we have proposed our conjecture for QED. So the question is it possible to do the same for the QED Lagrangian? Okay, so based on the gravitational case, we have proposed the following conjecture. The proper time asymptotic expansion of the, in this case, scalar QED effective Lagrangian admits an exact approximation which captures all the dependence on the electromagnetic invariants F and G. And the form of the factor is the Euler-Heisenberg-Lagrangian, but now the electromagnetic fields depend arbitrarily on space-time coordinates. In other words, we have proposed a new adiabatic expansion built from the previous one, and we have conjectured that if the prefactor is the Euler-Heisenberg-Lagrangian, the new coefficient associated with the new expansion will not have terms that vanish when the electromagnetic invariants are replaced by 0. So here you see the previous adiabatic expansion and the new adiabatic expansion. Okay, and here you have again the new adiabatic expansion with the new coefficients in Formula 7, and again the relation, or for the first time, the relation between the old adiabatic expansion and the new adiabatic expansion. So we have proposed our conjecture, but how do we check that our conjecture works? Of course, by computing the new coefficients over. So we have to compute them using formula A. So as you can see, what we do is to expand the Euler-Heisenberg determinant in the proper time. And then we group terms with the same order. For example, order 0 with order 0 with order 0, order 2 with order 2 and order 2, and so on. And finally, of course, we isolate the over coefficients. So what we have done is to compute all new coefficients until n equals 6, and we have checked that our conjecture is satisfied. That is, that the new adiabatic expansion does not contain terms that vanish when the electromagnetic invariants are replaced by 0. Okay, so more explicitly, here you can see the first 5 coefficients in orange. I'm not showing the 6th coefficient because it's super lengthy. And here I have highlighted the terms that have to disappear if the new expansion or if our conjecture works. So here the first important terms that appear in O2 and O4 are trivial. They have to disappear because the original adiabatic expansion has to match with the result for the constant case, that is with the expansion of the Euler-Heisenberg Lagrangian. So by consistency, they have to disappear in the new expansion. So the first non-trivial test of our conjecture appears in O5, where we have a term that goes like O2, that came from the Euler-Heisenberg Lagrangian, multiplied by O3 here. So if our conjecture works, this has to disappear. And then here you have the new coefficients, and as you can see, the problematic terms have disappeared. So by consistency, this has disappeared. These two terms have also disappeared. And the problematic term in O5 and the same for O6 have disappeared. Okay. So now we believe that our conjecture works, and we can ask ourselves, what are the consequences of the factorization? So why is it interesting to have this property of the one-loop effective Lagrangian? So first of all, I want to recall that with the factorization, we have captured a general non-perturbative property of the QED, of the one-loop QED effective Lagrangian, which is something quite interesting. But more specifically, the new expansion allows us to obtain some exact solvable cases. There is some new exact one-loop effective Lagrangian for other backgrounds. In particular, for a background consisting in an electromagnetic field pointing in the set directions that depend arbitrarily on the like-on coordinate, like you can see here, we easily find that except O0, which is 1 by definition, all the other terms of the new adiabatic expansions are 0. And therefore, the exact one-loop effective Lagrangian has this form that you see here. This is just the coordinate-dependent Heisenberg-Euler Lagrangian, but I have written it in terms of the electric and the magnetic field. That's why you see this form instead of the determinant that I showed you before. It's exactly the same. Another interesting case is the case where the background field is a single plane wave. In this case, the electromagnetic invariants F and G are 0, and therefore the one-loop effective Lagrangian is 0, so we don't have quantum corrections. This is also a well-known result, but now we have obtained it in a very straightforward way from the expansion. Okay, other interesting thing that we found is that our factorization, that is the factorization of the Euler-Heisenberg determinant of Lagrangian, seems to be consistent in presence of gravity. That is the case in the case when we have two background fields, the electromagnetic field and the gravitational field. And furthermore, in this case, it is also possible to perform a double factorization. So we claim that with gravity, we can also do this factorization, and this second factorization is ensured by a theorem given by Jack and Parker in this paper here. And finally, we can also extract some consequences regarding the Zwingen formula for reproduction, in particular because of the Euler-Heisenberg prefactor. We can say that the poles of the imaginary part of the one-loop effective Lagrangian that accounts for reproduction are located exactly in the same point than in the constant case. So in summary, as I have said before, the one-loop effective Lagrangian for quantum electrodynamics is in general unknown. However, we can always perform an adiabatic expansion of it, which is in general very complicated, but it can be done. And what we have done is to propose a new adiabatic expansion that captures in a factor some general and non-perturbative behavior of the one-loop effective Lagrangian for arbitrary backgrounds. The new expansion, or the good point from the new expansion is that it does not have terms that vanish when the electromagnetic invariants are replaced by zero. So we have captured some non-perturbative behavior, and the form of the global factor, as I said several times, is exactly the Heisenberg-Euler-Lagrangian, but with an arbitrary space-time dependence. And finally, thanks to the new expansion, we have directly obtained some solvable backgrounds, and we believe that our factorization is consistent in presence of gravity. So that's all, and thanks for your attention.
Yeah, thank you for your talk. Any question from the audience?
Hello, can I ask?
Yeah, sure.
Please.
Yes, I have a simple question. Is it possible to extract the imaginary part from your resummation expressions obtained for some models? I don't know.
The point is that we have resummed some part, but then we still have this adiabatic expansion. So we, in that sense, if we try to extract the imaginary part, maybe the information that we extract is not relevant. So the more appropriate thing should be like to partially sum other contribution, like the term that goes with the first derivatives, and then to obtain a explicit formula for reproduction. Because if not, it is true that we can do something, we can compute the poles like always, but since we have this adiabatic expansion, we have to be careful, because maybe since we it's always this trick, what should I do first, to integrate or to sum? Depending on this, the result should be different. So maybe in some cases it is possible, but you have to be careful.
All right, thank you, Sylvia.
Sylvia.
Thank you. Yes.
Christian Schubert and his collaborator applied string-inspired formalism, a kind of a pass-integral formalism, to compute interaction between photon electromagnetic field and gravitational field. Did you compare your result with their result? One. Yeah.
No, I'm not sure if I understand your question, but no, our results are not related with their results. You asked because of this statement, right?
Yep. The background electromagnetic field and gravitational field. There, Christian Schubert and his collaborators computed one law and expanded up to quartic order of Maxwell tensor and the super tensor. So you can compare your result with their result.
Okay. Well, I know a paper from Schubert, but from some years ago. Not. Oh, yeah. I think you are referring to the new one, no? The one based on his talk. Okay, so I have to. I didn't know the details. I don't know the details of the paper, so for sure I have to look to the paper and to see if everything matches. Thank you.
Any other question from the participant?
I have a question. If I
yes. Go ahead.
So first, thank you, Sylvia, for the nice talk. So the Euler Heisenberg model is also related with some other physical phenomena, like the birefringence phenomenon, for instance. So I'd like to know if the new results that you are presenting could affect the birefringence phenomena.
Well, I don't know. That's the first thing I have to say. But our results have to include this effect because they include the Euler-Heisenberg-Lagrangian. So if you look at the first term of the expansion, if you forget about the derivatives, those are the terms where you compute this birefringence and everything. So our results include this adiabatic expansion include the possibility to reproduce that result. But you are right that maybe these terms of the expansion or these terms of the expansion modify those results, but I don't know. But probably they change something. But I cannot say anything more specific.
Right, thank you.
Thank you.
Yeah, we should move to the next talk. Yeah, thank you, Sylvia.
Okay, thank you.
Now, Christian.
Thank you.
Christian.
Yes, here I am. Can you hear me?
Good to see you. Long time no see. Would you share your screen?
Can you see that?
Not yet. Just open.
Let's try again. Okay. Can you see now?
Yeah. Okay.
Okay. Thank you.
Yeah.
So thank you very much. I'm going to talk about Kerr black hole perfect MHD processes in Doran coordinates, which are horizon penetrating coordinates. And this talk is collaboration with Simonetta Filippi, Alessandro Lottini, Rahim Moradi, Remo Ruffini, Wang Yu, and Shasheng Sui. These are the main references I'm gonna use in this talk. This is our article on PhysRev, and it is based on papers of the 70s by Ruffini and Wilson and Damour. And what we are going to do essentially is to use horizon penetrating coordinates found by Doran in 2000 and to revisit essentially this physics of the 70s by using these new coordinates. The talk is organized in this way. I'm going to give you a review of Ruffini, Wilson, and Damour works. Then I'm going to introduce these horizon penetrating coordinates and then revisit the solution and having a physical discussion. And then we are going to give some conclusion. The starting point of the Ruffini-Wilson work is to use a Kerr metric. This is the standard one, and the main target is to find analytical solutions of MHD in general relativity. This is not a trivial task. So in the 70s, scientists had to use some sort of simplification in order to find this type of solutions. The starting point is to use Maxwell equations, you see on top, and we have to do some assumption. The first one is to have a perfect plasma, so an infinite conductivity you see in the center. Then you have to neglect pressure and magnetic force terms, and in this way, in this assumption, the fluid motion will be given by geodesic equations. And it is very important to notice here that geodesics have been integrated in the Kerr background, so one has analytical solution for the four velocities in particular. And so we are using these analytical results to build up this type of simplified solutions for the problem. We have to perform other assumptions. Then you have to take the phi and t components, the phi equal to 0 and the t equal to -1. In this way, the u theta quantity is a constant of motion. And so you can see the contravariant components of the four velocities in the Kerr metric given by those quantities. This is standard literature. So now the point will be to use these ones, introduce them in the other relations, and integrate Maxwell equations. Another assumption that one has to do in this approach is to require an overall neutral stationary and axisymmetric configuration. This means that one has got only the phi component only of the vector potential. You can see in the box what is the relation of the f of the Maxwell tensor in terms of this vector potential. And by using the perfect plasma condition, you can see that you can build up the various components of the Maxwell tensors. So from the perfect plasma condition, one can integrate in terms of the vector potential the equations and find an analytical solution of the phi component of the vector potential. You see that one, that is a function of theta and r, and that thing is given in terms of that integral you can see below. The integral is complicated, but by requiring, for instance, u theta equal to 0, the integral can become easier. So let's go on. When one has the vector potential, by introducing into the Maxwell equations, one can compute the forecurrent. Having the forecurrent, then one can compute charges. Essentially, what one has to do is to take the t-equal constant slices, then introduce the normal to that slice. You see that n mu, which is a non-geodesic and non-rotation-free time-like vector. And then by introducing the metric induced in the t-equal constant slice, one can compute the magnetosphere charge, essentially the charge of the plasma outside the black hole. You see that integral that you make. H is the determinant of the inducing metric. Then by making some standard manipulation, one can go on and find the charge of the black hole, because by using the Gauss theorem, one can show that and because of the fact that one has to have an overall charge neutrality by assumption, one can find that the Q of the black hole must be minus the Q of the magnetospheres. And then Ruffini and Wilson in their paper assumed, in order to induce a net charge in the black hole, that u theta must be constant in one hemisphere and minus constant on the other one. This is the way in which they got it. One can also compute Maxwell invariance for this type of solution. You can see the first and the second invariant. One is positive or 0, the other one is 0. Now, again, continuing in the overview of this work, historical work, we have to introduce further simplifications. We require u theta equal to 0, first of all. This implies that the Maxwell vector potential is a function of theta only. Then Ruffini and Wilson use this type of assumption that function f theta is essentially proportional to the modulus of cos theta. E0 is a constant. And then by computing first and second derivatives in theta, one has got the standard Dirac delta quantities. Now the new part of the work. So this is the review. What we're using now are essentially these new coordinates found by Doran. These are horizon penetrating coordinates and are extremely important both in analog gravity for the acoustic black holes, because when you study acoustic black holes, essentially black holes occurring in fluids, in ordinary fluids, so that the speed of light is replaced by the speed of sound. The equations of hydrodynamics naturally use this type of coordinates first. Second, this type of coordinates, horizon penetrating ones, which are coordinates which do not break on the horizon, so allow you to enter inside the black hole, are extremely important in numerical relativity because of excision. The point here is that historically there has always been a problem which boundary condition give to the partial differential equations of the fields on the black hole horizon. By using horizon penetrating coordinates, you completely not consider this problem, because you enter inside the black hole and then you give whatever strange boundary condition inside. Because of the direction of the light cones, nothing can come out. So in this way, you avoid completely to give boundary conditions on the horizon. So they are extremely important. In particular, I'm going to show you these Doran-Pan-Levé-Gould-Strand coordinates. I call them DPG, and the mapping which connects Boyer-Lindquist coordinates and these new coordinates. You see that relation you can find below. And in this way, by using this type of coordinates, the metric the Kerr metric becomes this one. It's more complicated because you have more of diagonal terms, but physically it's got several useful aspects. In particular, here in the following, I'm gonna replace R capital and theta capital with R small and theta small because they've been untouched by the coordinate transformations. So you can transform the vector potential, you see, that is the form. You can transform the 4 velocity, and that is the relation below. In the U theta equals 0 case, everything becomes simpler. You see the 4 velocity, which has become much easier. This is essentially, this mu is the T-wall constant normal geodesic observer, and the interpretation of T capital is the local proper time of observers in free fall along trajectories of constant T, theta, and phi. In these coordinates, the Maxwell tensor has got one component only, the invariance you see below. But the important thing, and now that the physics comes, is that by using these coordinates, introducing a tetrad, essentially a local Lorentz frame adapted to these coordinates and to this normal observer, you can see that the Maxwell tensor in this tetrad has got only one component of the magnetic field. That one you see in the center of the page. So what you see is that electric field is 0 everywhere, and this is expected because from initial hypothesis of perfect plasma, infinite conductivity, one should not have the electric field. And in particular, we know that from plasma physics, there must exist a frame in which charge density is 0 everywhere. And by using all this formalism, you can immediately compute this one. Let's see now. This is the for current in this new set of coordinates. You see that the zero component, the time component is 0. And you can compute immediately the current lines. And here is the physics. On top, you can see the current, by integrating the current lines of this solution in the horizon penetrating coordinates. You see there is no twisting, and you can continue the current lines inside the event horizon because you are using horizon penetrating coordinates. The fact that there is no twist is because you are essentially falling with the plasma. Below, instead, you can find the same plot, but in Boyer-Lin twist coordinates. And you can see that you cannot go in, first of all, because the horizon break up on the the coordinates break up on the horizon, and there is a lot of twisting. Then you can compute the charge density for vector current, and you can immediately check that the charge density is 0. So summarizing, what we've done is that we are measuring everything sitting on the plasma, and so physics becomes much easier. We can study also the electromagnetic energy stored outside with the standard tools. We did that with the U theta equal to 0 case. We take a slice, T equal constant, higher surface, and you can compute the energy, which is, you see, very simple in this formulation, very nice also. This quantity, of course, depend on the cut, so it's a quasi-local quantity. So what's next? Well, the first, and this is the last slide, essentially. We sit on plasma and we found very nice thing, but we didn't find the charge on the black hole. And the main reason is that in order to have charge, one must have that constraint on U theta, but we required an U theta equal to 0. And the problem is that we have not an equivalent of Doran coordinates adapted to this problem, because Doran coordinates were adapted to the U theta equal to 0 case. So in future, it would be extremely important to continue and find the equivalent of Doran coordinates in this case of these horizon penetrating coordinates. And second, it would be extremely useful to revisit other analytical solutions of the past by using these coordinates, because many results were found in the 60s, 70s, 80s, but these coordinates came in 2000. So it would be extremely important to use them and to reinterpret the old physics by using this new tool. Thank you very much.
Yeah, thank you for your interesting talk. Any question from the audience?
I see. Professor Kadir. Professor Kadir raised his hand.
Ashka, yes, yes, go ahead.
I cannot hear you.
Please unmute. Asha?
Yeah, okay, it's gone again.
Yeah, okay.
Yes.
We can hear you.
Now, I was wanting to ask about the approximation of the pressure being negligible. What's the physics behind that? Because you're using J non-zero, then why is it becoming negligible when you use
I mean,
J?
this is an assumption historically in order to get an exact solution. Of course, this is a toy model. More realistic models require the pressure, but in this case, if you don't set up the term equal to 0, you are not able to go on.
But my problem was of consistency of approximations. Later on, you're using terms that have the J, and it's not obvious to me that those can be taken and the J with the P be neglected. So where you have that pressure neglected, I don't see the consistency across.
We did some estimate of that case in the article. Somewhat there is a consistency. If you put some numbers, you can see that you can do them, but of course it remains a very strong assumption.
Okay, thank you.
Thank you.
Any other question? If not, then let us thank Christian again. Guilio?
Hi, can you hear me?
Yes, yeah. Would you share your screen?
Yeah, sure. Can you see it?
Mm-hmm. Yes, yes.
Okay.
Yeah,
so
good.
Today I'm going to talk to you about electromagnetic and gravitational radiation from moving particles. I apologize, I will go really fast on the electromagnetic part, which is the bigger part, and just give some some little piece of work about the gravitational part, because it's still all a work in progress, and I don't want to give results before the time. So a little introduction. Any electromagnetic charge, any charged particle which moves, creates an electromagnetic field, and with this field it creates a radiation. This is the basic formula by which we can find the spectrum of electromagnetic radiation from a moving charge. And this is found in many different textbooks like Jackson and so on. Under some really sensitive hypotheses, we can redefine this spectrum in this way. So we just need to calculate the Fourier current. So this is the this is the Fourier current defined by the particle. By the way, the Fourier components of the current. And of course, in order to have a radiation, we need the particle to be accelerated. And this is the same as the gravitational field. Constant velocities, we have no radiation, but for accelerated particles, we can find some radiation. One can think about the field of moving particles in the following way. This is just special relativity, because with simple computations, one can see that the longitudinal parts of the fields remain the same under Lorentz boosts, while the transverse components are increased. So in the limit in which the particle goes to the speed of light, we can think about a plane wave. of course, is just a way to think about it, because we have a mass, so it is not a photon, it is not a plane wave, but the field is really, really similar. A problem we took into account is the problem of radiation reaction, which is a problem, was one of the most controversial topics of the last century, and nowadays it is still a problem. Here I reported a self-energy diagram. Of course, here I done everything on the classical level, so there is nothing quantum. However, this is a way we can see what happens. When a particle moves, it generates a field, and this field acts on the particle itself, and this is what's so-called radiation reaction. And there is no a really satisfying way to deal with this radiation reaction. In 1938, Dirac described this motion of an electron under the action of its self field with this equation, the so-called Lorentz-Abram-Dirac equation, which is derived by really strong hypotheses. So substantially the conservation of energy momentum tensor, but it is still full of problems, because we have third derivatives of coordinates, and we have pre-accelerated solutions and run-out solutions, so many different problems. A way to deal with it is the so-called Landau-Lifshitz proposal. So we can do an approximation, because if we go to the particle reference frame, we can see that the self reaction is ever really small compared to the classical Lorentz term. So we can substitute in the Landau in the Lorentz-Abram-Dirac equation the derivatives of the velocity with the usual Lorentz term, and this gives this equation. I really want to stress that this equation is classically exact, in the sense that, of course, it is an approximation, but any further correction to this formula will be smaller than a quantum correction. So if we stay in the classical regime, this is classical, this is exact, and this is what we consider. A really quick introduction to gravitational radiation. Of course, we know that the basic equation in gravitation is the Einstein equation. Here, R mu nu is the Ricci tensor, and R is the Ricci scalar, and T mu nu is the energy momentum of the source. Of course, the gravitational field, as we know, is quite different from other fields, because whenever we are describing it, we are describing something which is at the same time the actor and the background of our story. I can say something like this, which is really more difficult than a usual field with a classic background. However, of course, we can do some approximations here, and the most useful one whenever we are talking about gravitational waves is the so-called weak field approximation. So we can expand the metric as a flat component and a perturbation. Here the perturbation is h mu nu, and we will work with this h mu nu and see what we can find. In a specific gauge, the so-called harmonic gauge, the Einstein equations became really simple, because it became substantially a wave equation in the perturbation. So here S mu nu is just a combination of the energy momentum tensor, so this is just a wave equation. Of course, this equation can be solved implicitly with a green function, which is just the green function of the D'Alembertian operator, and this is the final form in which we can put our solution. So this is just a retarded green function which brings the effects of the source from X prime and tell us what happens in X. With this a little bit of calculation, and this is done in many different textbooks, we can find the formula of the gravitational spectrum with respect to the K. Here, K is of course the form momentum associated to the radiation, to the gravitational radiation. Now, I have to underline the fact that the source of gravitational radiation is every source of energy and momentum. So whenever we consider, for example, an electromagnetic system, we will have, of course, for example, a particle which has his own electromagnetic tensor and his own energy momentum tensor, but also the field produced by the charge and even the fields of the background, if there are some fields. And this is the case, for example, in a simple example I will show you later on. Now I will go really, really fast through the calculations of nonlinear Thomson scattering. So this is just the collision between a particle and a laser field, a really strong laser field, including the radiation reaction. So this is why I give a little introduction to radiation reaction problems and to electromagnetic radiation. So whenever we are dealing with a plane wave, and we can construct a plane wave which is really similar to a laser field, we can expand everything with respect to a phase, which is this product. Here, K0 is the form momentum associated to the laser field or to the plane wave. And we can work in a Lorentz gauge plus these conditions, so the scalar potential equal to 0. We can do this because we are working in vacuum, and this is allowed. And the interesting fact is that in 2008, Antonino Di Piazza, my supervisor, found the exact analytical solution of the Landau-Lifshitz equation in the case of a plane wave background. And this is the solution. This means that we can do all these calculations analytically without any further approximation and see where we can arrive with this hypothesis. Here there are many different quantities. I don't want to go into the detail because it's useless at this level. One thing I just want to stress is this formula H, because the radiation reaction effects are encoded in this function, namely in this term here. And this is interesting because here Xi is proportional to the derivatives of the field, of the background field. So is a we could say is a measure of the strength of the background. And we can see that the radiation reaction effects are defined as an integral, so a cumulative effect. And this is in agreement with how we can think about radiation reaction effects. So something which is cumulated through the trajectory of the particle. Everything is done in a light cone basis, which is just a really useful base in this case. And here I will be really, really fast. We've done the calculation. It has a two phases integrals. So this is the gravitational, this is the, I'm sorry, the electromagnetic spectrum. And what we found is a formula like this one, which is quite obscure, I see. In fact, it is full of different terms, and it's not really easy to see something in this formula. The interesting fact is that we can do an approximation at this level because there is a so-called local constant field approximation. Whenever we are considering really fast particles, we can do this approximation and expand in this difference between the two phases in the previous integral. So this phi minus, we can expand in phi minus and find an expression like this, which is really, really compact. And with further calculations, we found this final form. So there is this electromagnetic radiation as a single integral in a phase and Bessel function and so on. Again, I apologize not to show a graph. However, the interesting thing is here is again this h² function, and the fact that whenever we go h equal to 1, we represent the formula, the existing formulas without radiation reaction. Now, I just want to spend the last minutes talking about a curious relation between the electromagnetic and gravitational spectra. Back in 70s, Nikishov and Ritus showed that under certain circumstances there is a relation between the gravitational and the electromagnetic radiation. Here is the relation, because on the left hand side we have the gravitational radiation, and on the right hand side we have this modulo of J mu squared, which is just proportional to the electromagnetic radiation. And this is the proportionality coefficient. Here m star is just the mean kinetic energy of the charge in the average rest frame, is a constant. And this is interesting because we have a relation between two really different effects. And we will consider in the last slides a case of strong constant magnetic fields as a background. And we will see that we find some poles in k². K is the Four momentum associated to the gravitational wave. And we will try to give an explanation to this. So we consider a motion in a uniform magnetic field. Of course, we have motion in circles, and the background magnetic field is static, is infinite in extent. So this is our hypothesis. And we will consider the gravitational radiation produced by the background field combined with the self field produced by the charge. So this is the interesting effect. We have the charge which creates a field, the field which interacts with the background magnetic fields, and we will see what happens. So the electromagnetic tensor is defined as usual, and we will divide it into two pieces. One is the external one, and one is the self one. So this is connected to the background magnetic field, and this is connected to the self field. Now, the general expression of the energy momentum tensor of an electromagnetic field is this. And here we see we have three possible combinations, because F mu nu is defined as a sum of the external and the self field electromagnetic tensor. Of course, the background magnetic field by itself cannot produce any radiation because it is static, it is uniform, and we have no radiation. The self field with itself could produce some radiation, however, it is negligible. So what we consider here is the electromagnetic tensor produced by the cross term between the self field and the external field. And this is it. We can expand in this form the self field electromagnetic tensor, and the external momentum energy momentum tensor is simply found because it's just a constant times a delta. And after some calculation, what is found is this formula. So here, of course, is symmetric. We have Bessel functions, but the interesting part is this pole. As we see, we have this pole, which comes from this expression of the self field electromagnetic tensor. And I will tell you in a second what I think about this. Of course, here there is the term which gives the gravitational radiation, but the trace of energy momentum tensor here is ever zero. So we only need this term. And we compute this term with this result. And what is found is exactly the proportionality gives at the beginning of the article. So this one. And I would try to explain what Ritus and Nikishov said substantially. We have a pole expansion of the result, because of course this pole will give k to the square at the denominator and k to the second. And we have these poles because we have an infinite background. And what we can think about this in the following way. I will use a quantum language, and of course we are classical, but it's useful to think about it in this way. So we have the charge which moves and generates a photon, and the photon can interact with the background magnetic field and can be converted to a graviton. And this is allowed by classical mechanics. The fact that we obtain these infinities is because we have an infinite in extent background field. So there are an infinite space in which the photon can be converted to a graviton. However, we take the leading term of this expression, and we see that there is this proportionality. Now, what we are doing now is try to find the gravitational radiation in nonlinear Thomson scattering. So the first part of this presentation was published some weeks ago and a week ago. And now we want to see if whenever we consider gravitational radiation, we get this relation, and what happens if we take into account all the radiation reaction effects. So this is my conclusions. We found the analytical and exact on a classical level spectrum of nonlinear Thomson scattering. And I just show you all the results about the proportionality between the gravitational and the electromagnetic radiation. What is still to do, of course, is to find the complete gravitational spectrum generated by a nonlinear Thomson scattering, see if this relation between the two spectra is still valid in this case, and maybe what happens if we go to the quantum regime. And this is all we are trying to find. Thank you for your attention.
Yeah, thank you for your talk. Any question from the audience?
Can I go ahead and ask a question? Yeah. You seem to be using the assumption of quantum gravity because you talk about gravitons on shell. You're doing the whole calculation like a Thomson effect with gravity. Now, quantum gravity, there is no theory that I know of, so I'm not really clear how one can go with an assumption of this type. We're not going to be able to see the effects as yet. Orders are totally different. So that was my question.
Yes, of course. Well, this is of course a sensitive question because I spoke about gravitons and so on. I didn't really mean gravitons in the sense that in the Ritus and Nikishov paper, they called gravitons something which is absolutely classical. So all these calculations are done on a classical level. I spoke about gravitons just to explain these effects of radiation, electromagnetic radiation, which is converted to gravitational radiation when it interacts with the background. And they explained as a quantum, I think, quantum language, but it is still all classical. So any calculation here is classical, and we have no loop quantum gravity, we have no quantum gravity whatsoever. Of course, a further step could be to introduce some assumption and try to go maybe on the tree level, on the one loop level, to quantum gravity. However, here is still all classical.
The semi-classical works where we know that there is a good quantum description. You do semi-classical analysis for electrodynamics, and it makes sense because we know of quantum electrodynamics that works. I don't know of a quantum gravitodynamics that works. And so I don't know that there is such a thing as a graviton, a nonlinear graviton. One assumes and one can try to do things, but then one really has to see how that would work. When I go to something like a Thompson scattering, I have not a clue that there could be the non-perturbative effects made into perturbative effects. It's just totally a different level of approximation there. That the assumption, I don't see how it works. Well, thank you.
Oh, thank you.
Okay, yeah. Thanks for your question and also for talk. Shall we move to the next talk? Susmita Yana?
Yes.
Would you share your screen?
Yes, sure. Can I see?
Not yet.
Can I see my screen?
No, actually, we see only the window display, not PDF. Not PDF yet. Yeah.
Can you see now?
No.
Okay, I'll try again.
Yeah. Yes, yes.
Oh, okay. Yes. Can I start now?
Yes, yes, please.
Okay, thank you. Hello, everyone. I'm Shushmita, and I'm currently doing PhD from Indian Institute of Technology, Bombay. So today I'll be talking about my current project, and it's about constraints on the non-minimal coupling of electromagnetic fields from astrophysical observations. Let's begin with the motivation. So we all know that electromagnetic field is an important source of astrophysical observations for testing different theories of GR, both in strong and weak gravity regime. In order to do that, we usually consider the non-minimal coupling of electromagnetic fields, where we consider Maxwell's action written in terms of a covariant derivative instead of a partial derivative. And those theories are well tested in weak gravity, but not yet verified in the strong field sector. Hence, we want to raise a question that how to verify that the minimal coupling of electromagnetic field is accurate or not. For doing so, we want to start with a non-minimal coupling and see that if it is possible with a better observation, whether we can test the non-minimal and minimal coupling of electromagnetic field. Okay, so for doing that, there is a observational setup, and I have considered this image from this reference. Here you can see the authors have shown that some bunch of photons are coming from far away and getting deflected by this gravitational attraction of black hole. And here, and we planned from here that by measuring these deflection angles of photons, if it is possible to put a bound on the coupling coefficients present in our theory. Okay, so there are more I need to say about this diagram, and I'll come back to it later at some relevant point. Okay, now let's move on to the next slide. So here I have shown the action for non-minimal theory of electromagnetic fields, and this is the most general the most and and it includes non-minimal coupling between electromagnetic fields with electromagnetic fields and Ricci scale model in 2002 for studying existence of birefringence of the vacuum. And but these models are quite complicated to handle, and that is why there is a simpler version of these you can see that electromagnetic field and Riemann tensor is present. Okay. And after a few years, in 2003, Prasanna and Mohanty considered this model and studied it with a Schwarzschild metric to see the effects of a static black hole on the nearby photons. And they got a modified dispersion relation from that instead of the usual dispersion relation p square equal to 0. And they from there they calculated the arrival time of photons and obtained the constraint on these lambda coefficient, and they found it of order 10 to the 20. But what I think that their calculation was restricted for a black hole in static universe. In reality, all the black holes are dynamical in nature, and they are kind of immersed in the expanding universe. And that's why we want to do a similar analysis with a dynamical black hole instead of a static one. For doing that, we consider Sultana-Dyer metric, and this metric describes a expanding black hole, which is expanding black hole in the asymptotic background of the Einstein-de Sitter universe. Okay, here you can see that this is a product of Schwarzschild metric and time-dependent part, which represents the expansion of the background universe. So we have from this metric we have rewritten this metric with these quantities, these r tilde and t tilde. Here all these two quantities are dimensionless. Here this H0 is Hubble constant and m is the mass of the black hole. And T0 tilde is also dimensionless, where this alpha 0 is dimension of length, and beta 0 is also dimensionless. So with these definitions, we have rewritten this metric like this equation 6, where this ds tilde square is given in equation 7. For rest of our calculation, we will be working with this equation 7 with this metric. Okay. From that metric mentioned in equation 7, we have considered the symmetries present there, and we found two of them. One is for sorry, one is for temporal one, and another is for the azimuthal symmetry. And these E tilde, this conserved quantity, can be related to energy of photon, and this L tilde can be related to the angular momentum of the photon. and both these things are conserved with respect to the affine parameter. And after that, we have defined few symbols as well, just to make the calculation simpler. Now let's proceed with the main calculation. So we have taken the Prasanna's calculation and obtained this equation of motion. So from here, after this, we have switched to a local inertial frame instead of the actual non-inertial frame, and used Bianchi identity and econal approximation as well. And we and that lead to this equation of motion. As you can see that this equation includes equation of motions for different components of j equal to 1, 2, and 3. And this epsilon is the product of Riemann tensor and momentum of photon. Everything is written here in the local inertial frame. This inertial frame. From here, I have calculated the equation for 1 and 2, and using them, they are two dispersion relations for photon. And you can see that these are modified dispersion relations photon, and one of them is cubic nature. And this cubic equation I get because I worked with a dynamical black hole, whereas Prasanna and Mohanty did a similar calculation with the Schwarzschild metric, and they obtained a modified dispersion relation as well. But that is only quadratic in nature. Okay, hence, at this point, I can conclude that just considering a dynamical black hole, we are getting a higher order dispersion relation, and that is something new. So from these dispersion relations, these quadratic equation, we plan to obtain the deflection angles of photons for different polarizations. As you can see in this diagram also, that the authors have represented deflection angles for different polarizations, and we plan to calculate these polarization dependent deflection angles and get a bound on the coupling coefficients present in our theory. Okay. So we have done the calculations. We have calculated the deflection angles for both Sultana diametric and Schwarzschild as well, and obviously with the different polarizations. And we expanded all these quantities about these dimensionless quantity d. Okay, d is a very small number, and the definitions of these 1 over beta 0, and beta 0 I have defined earlier as well. Now here I have shown the plot for the deflection angles for Sultana diametric. This one is for plus polarization and this one is for minus polarization. And you can see that both the curves look similar, but their values are different. And we have done the plots with different values of B, and B is we are considering B as a parameter of our theory, and B is defined as a ratio of L tilde and E tilde. Now after these, I have shown the plots for difference between two deflection angles for different polarizations, and here you can see that for Schwarzschild this quantity is 0, but for Sultana dar, I mean for the dynamical black hole, this is non-zero, and these three represents curves for different values of B. Okay. Now let's come at the final result. So what Prasanna and Mohanty did, they calculated the arrival times of photon coming from sun, and they put a bound on the difference between the arrival times for two polarization dependent. They put a bound on the difference between two arrival times for two polarization, and they got the bound as of order 10 to the power 20. Whereas we have calculated the deflection angles for the dynamical black hole, and we didn't put any further constraint on the deflection angles or what. And from the expression itself, it depends on the calculation also. Not depends. Here I didn't show the entire calculation, but from the expression of the deflection angles, we got some terms, some relevant terms, and we got these constraint on lambda. And considering the M87 black hole, we have got this constraint on lambda, which is of order 10 to the power 14. So here we have got the improvement of order 10 to the power 6, which is fine again. So this is the final result, and now let's come to the conclusion. So for our entire calculation, we have assumed that our black hole is spherically symmetric and non-rotating, but in reality, the black holes are not non-rotating. That is why we plan to extend this work with our rotating dynamical black hole, and we hope that we will get a far more tight constraint on the lambda. Thank you for paying attention.
Yeah, thank you for your talk. Any question from the audience? No question? Then shall we move to next talk? Somebody correct car? Would you share the screen? He's not here yet. So may I switch it to last talk? Shrishti Agarwal, are you hearing me?
Yeah, I can. I'll share this one.
Would you give a talk first? Then we can wait for Samved.
I have no problem with both the things. What shall I do then?
Please share your top file.
Okay.
Yeah, presentation. Yeah. Yeah, share your screen. Yeah, you're
sharing this.
Okay. Yeah, good. Yeah. Yeah, thank you.
I have to start my video, but it seems. Shall I start?
Yeah. Fine.
Hello, everyone. Today, I'll be discussing about dynamics of relativistic electron in non-uniform magnetic field and how it is useful in astrophysics and quantum computing. So before starting with the main topic, let's revise what happens when the electron is in uniform magnetic field. So when electron is confined to the plane perpendicular to the magnetic field, its energy level discretizes and becomes degenerate. The lower level becomes non-degenerate, and the other levels become degenerate. This is a very famous phenomena which is called Landau quantization, and the energies levels are given in non-relativistic by this formula, and in relativistic the energy is directly proportional to square root of .
Network seems to be unstable. I cannot hear you.
Hello, Kim. Kim, I don't understand what happened. Am I not able to share the screen?
Yeah, would you share again?
Okay, sure. So where did I left? I was just speaking and I didn't realize this.
Sister, you have to share again. It is unshared now.
Yeah, I'm sharing. Is it visible?
Yeah.
Yes.
Yeah.
Okay. So from where should I begin? Did you hear about this Landau quantization applications? Hello?
Yes.
No.
Yeah.
Okay, so I'll just begin with the introduction of Landau quantization. Okay. So when electron is confined to the plane perpendicular to the magnetic field, its energy level discretizes, and this phenomena is called Landau quantization, where the energy of these levels are given by the formula given here in non-relativistic regime, and in relativistic regime it is given by this formula. Landau quantization has been very useful in explaining many of the effects in both relativistic as well as in non-relativistic regime. In non-relativistic regime, they have been useful in many condensed matter experiments through quantum Hall effect, de-Haas-Van Alphen effect, Shubnikov-de-Haas oscillations, whereas in relativistic regime, it leads to the modification to equation of state and Super-Chandrasekhar-White dots, and also onset of neutron drop point. But the problem is that this Landau quantization has been considered only in uniform magnetic field. So, and the compact objects as well as in plasma, whatever the field is, it is never uniform. This leads us to ask the question, what happens if the magnetic field is non-uniform? So to solve this, first let's appropriately choose the magnetic field profile. Our magnetic field should be in accordance with the Maxwell's equation, and the gyromagnetic radius should be comparable or less than the Compton wavelength of electron. Also, so to deal with the plane and one-dimensional equation, we choose the cylindrical coordinates such that our magnetic field profile is given by the formula, this formula, where n is the variability index and rho is the radial component in cylindrical coordinates. So when n is less than 0, we'll have a decreasing magnetic field, and when n is greater than 0, we'll have an increasing magnetic field. Further, we solve the Dirac equation by choosing appropriately our vector potential and our wave function chi, such that our Dirac equation solution, to solve the Dirac equation, we have got this differential equation, where lambda is the Compton wavelength of electron, k is a constant, m is the azimuthal quantum number, alpha is the eigenvalue of this equation, and it is equivalent to this value for uniform case. And so in general, E is equals to mx square root of 1 plus alpha. Also, coming back, this equation resembles the Schrodinger equation in one dimension in Cartesian coordinates. This term could be equivalent to kinetic energy, and the remaining term is equivalent to the effective potential. So this effective potential, when we plot for different n, you see that this has, when n is greater than -1, this has both the attractive region as well as the repulsive region, whereas when n is less than or equal to -1, it has only the repulsive potential. To have the stable solutions, we solve for the cases only dealing with n greater than -1. Let's see what happens to our eigenvalue spectrum when we have an m is equals to 0. So the spectrum looks like this. So as we know, the uniform magnetic field, the eigen levels are all degenerate, but when n is not equals to 0, this degeneracy is broken. And you see, when n is negative, the spin up of lower level lies above the spin down of the higher level, whereas the opposite is true when n is greater than 0. Not only that, that it lies above the lower level, upper level spin down. There is also very interesting phenomena that is coming up next, is the spatial alignment, the spatial relative differences between these two levels. So as n decreases, you see the difference between these two levels increases, and when n is further close to -1, there is so large variation here that the lower level spin up lies close to the second higher level of spin down. Further, it may close to merging with the second higher level of the spin down. So you see that there may be some kind of degeneracy depending on the magnetic field profile or the appropriate choice of n. This gives the general value of the level eigenvalue for given n value, where C1 and C3 are the constants and these are functions of n. Okay. Let's see what happens when m is not equals to 0. So for uniform magnetic field, just for a recap, what happens is when m is 0 or any for positive m, these eigenvalues remain same. But when n is different, again, the eigenvalues differ, and there is a separation between positive m and 0m, which increases with the decrease in n. Well, this is owes to the ease of rotation of the particle in the direction of magnetic field when your field is decreasing. So to summarize, Landau quantization in non-uniform magnetic field leads to the breaking of spin degeneracy, spatial alignment of spin levels, and which depends on n, and reduction of energy for positive n if magnetic field is spatially decreasing. Thus, this is very useful to attain the desired energy spectrum, as we can modify our n and m so that our energy levels could align in a special desired way. Now let's come to its applications part. As the title says, we'll be discussing the applications in two regimes. One is the astrophysics, the other is the quantum information. So let's discuss about what happens in magnetized white dwarfs and how this is useful in this region. So white dwarfs, we know that white dwarfs are n phase of stars consisting of electron degenerate matter, and their maximum mass is given by our famous Chandrasekhar limit of 1.44 solar mass, provided they are non-rotating and non-magnetized. However, in the last 2 decades, there have been several overluminous supernovae, which seems to suggest super Chandrasekhar mass white dwarfs as their most likely progenitors. So to explain these super Chandrasekhar mass white dwarfs, researchers use magnetic field as the tool. Note that magnetic field can have 2 effects. One is the classical effect, that is through Lorentz force, and the other is the quantum effect, that is through the Landau quantization. And people have worked in both of these to account for these high mass white dwarfs. But the problem is that the Lorentz force happens when the magnetic field is variable. And for Landau quantization, we know that it is only known for the uniform magnetic field. Hence, therefore, we thought that is a main point of thinking, that to solve the Landau quantization in the non-uniform magnetic field, so that we can tackle these 2 things together to answer these super Chandrasekhar mass white dwarfs. We appropriately choose the magnetic field profile within the white dwarf such that it is constant in the center and then field decaying. We further solve the magnetostatic balance equation and mass conservation equation. Note that this term owes to the Lorentz force, dV/dr by b square by 8 pi, and P as a function of rho e, P, where P is the degenerate pressure and rho is the degenerate matter density, is modified through Landau quantization. So let's see how it gets modified. So black is the Chandrasekhar equation of state. Now, when you have different n and high magnetic field, note that the equation of state becomes softer in the low density regime and stiffer in the high density regime. Further, if you just keeps on lowering the magnetic field, the equation of state merges with the Chandrasekhar equation of state. So that is the discrepancy, that if we have high magnetic field, we can no longer use the Chandrasekhar equation of state. We have to use the modified Landau quantization equation of state. And this definitely gives you the high masses. The masses here is around 2.5 solar mass, which is actually the regime of the observed masses of between 2.1 and 2.8 solar mass. We also compared that it is the main effect of Landau quantization, or is it the main effect due to Lorentz force. So once we have plotted the Chandrasekhar equation of state with Lorentz force and found the masses, we'll see that the masses do not cross the Chandrasekhar mass limit. But only when we take the Landau quantization into account, we can account for the super Chandrasekhar masses. Hence, it shows the role of Landau quantization in explaining the super Chandrasekhar masses. Now let's move to the second application, that is the quantum speed of electron. So quantum speed of electron is the speed of transition from one level to another. Imagine these are two levels. So electron is presently in the ground level and it has to make a transition from one level. So let's first understand briefly that how is it related to quantum information. So these levels are equivalent to the qubit states, and if you want to have information stored in qubits and then change its information, so it naturally requires the electron to transit from its one state to other. Thus, the speed of transition of electron directly determines the processing speed of quantum computers. And see that the electron cannot transit at the infinite amount of time. It is small time. Its time is limited by the Heisenberg uncertainty principle. Moreover, it also makes a displacement radially while making this transition. Hence, we can compute its velocity as a speed as the ratio of its radial displacement to the time it takes for the transition, where the T minimum, the time, is given by the Mandelstam bound using the Heisenberg uncertainty principle in 1945. And given our original magnetic field profile, when we compute the speed for different n, we see that for uniform magnetic field, which owes to n is equals to 0, and for an increasing magnetic field, there is a definite increase in quantum speed of electron. The solid lines here represent the upspin of electron, whereas the dotted line represents the downspin of electron. So we see that for the downspin, there has been a decrease with n, whereas for upspin at least, you will see an increase in the quantum speed of electron when you have an increasing magnetic field profile. The top figure shows the main relativistic regime and the bottom figure corresponds to the non-relativistic regime. And in both the cases, with the increase in magnetic field, with the increase in n value, we see an increase in the quantum electron. So to summarize, Landau quantization in variable magnetic field, it lifts the degeneracy of level, it modifies the equation of state, and also accounts for super Chandrasekhar mass. It further increases the quantum speed of electron for positive. In future, we are looking for the laboratory observations of energy spectrum and want to explore for other applications of Landau quantization in non-uniform. Thank you.
Yeah, thank you for your talk. Any question from the audience? Yeah, thanks for your talk, Shrishti. Some better here. Some better collector here. Some better collector. Yeah, he's missing. So this strong field session 2, a strong electromagnetic field and gravitation field in astrophysics and cosmology. Now the second session had only 9 talks. Some bad collector is missing. So do you have any question to speaker still participating this Zoom meeting? No response. All right. Thank you all the speakers of this session and all the audience for your participation and wonderful talk. Yeah, thank you so much.
Yeah, thanks for organizing the session.
Thank you.
Christian, are you attending 17th Italian Korean Symposium, the first week of August? Online?
No, I'm sorry.
Oh, I see. That is online for international part. And for Korean side, yeah, my university will host, yeah, on-site meeting. Yeah. Shisheng? Are you hearing me, Shisheng? Shisheng? Yeah, Tiago? Tiago, are you hearing me? Okay, then I'll close this session.